We're dealing here with the problem of the photoelectric effect. And our formula for this situation is that the maximum kinetic energy of the escaping electrons is equal to the energy of the photon that's incident minus the work function. Okay, now we're told here that the work function is 2.24 eV, and we're told that the wavelength of incident light is 425 nanometers. Okay, so the energy of the photon here, that's given by hc over lambda, right? So 6.626 times 10 to the minus 34, and then the speed of light, and I divide by that wavelength, 425 times 10 to the minus 9, and I get 4.68 times 10 to the minus 19 joules, which works out to be 2.92 EV. Okay? Now, we're interested in finding the maximum velocity, so that's related to the max kinetic energy. So the max kinetic energy here, which is 1/2 mv squared, that's equal to the energy of the photon minus the work function. Okay? So that's the amount of energy the electrons have left over when they escape the metal, which is 0.68 eV. Now, if I'm going to solve this for velocity, I've got to convert this into MKS units. So 0.68 eV, that's 1.09 times 10 to the minus 19 joules. All right? Now, I'm going to set that equal to that kinetic energy. Now, the mass here is the mass of an electron, which is 911 times 10 to the minus 31 kilograms. Right, so now all I'm going to do is solve for V, my only unknown, and V is 4.90 times 10 to the 5th meters per second. Safely below relativistic range, so I don't have to worry about any of that stuff. Okay, so that's part A. We found the maximum velocity that the electrons escape. Now, if the energy of the photon had been less than 2.24, if it had been less than the work function, you can't have a negative kinetic energy. So that would have meant that the photons don't escape, or that the electrons don't escape. All right, part B, it asks for the cutoff wavelength. Well, the cutoff wavelength, that means, the cutoff wavelength means the electrons barely escape. And so the maximum kinetic energy of the electrons that escape is 0. And so we set that equal to the energy of the photon minus the work function. That means the energy of the photon is just equal to the work function. Okay, so we got to find the photon energy where, it's going to have an energy of 2.24. So we're going to set hc over lambda cutoff equal to 2.24 eV. Okay, now I got to convert everything into, well, okay, so lambda cutoff is going to be hc over 2.24 eV. But see, I've got to get all this stuff into MKS units. So there's my h, there's my Planck's constant, 6.626 times 10 to the minus 34. There's my speed of light, 3 times 10 to the 8th. And then 2.24 eV, that works out to be 3.58 times 10 to the minus 19 joules. Okay? And if I multiply all this out, I get 5.55 times 10 to the minus 7 meters, or 555 nanometers. So there's my answer for the cutoff wavelength. And right, and since the wavelength of light here is 425 nanometers, that's less than the cutoff wavelength. That means that these photons are more energetic than the cutoff wavelength photons, which means that the electrons should have some energy left over after they escape. So everything seems to hang together in this solution.